One of the most important convergence tests is the ratio test, and the only condition that we must have is that all the terms are non-zero. So as long as you don't have a term that's equal to 0 in your series, this test can be used. So the assumption is that if we have a series from k equals 1 to infinity, and the issue isn't that it's from 1, but it's just some series, and there's a rule for that series, we'll call it a of k, and there's no non-zero terms, then what we're going to focus on is the limit as n goes to infinity of the absolute value of the n plus 1 term to the nth term. Notice this would be no different than looking at the limit as n goes to infinity of the n plus 1 term times the reciprocal of the nth term. Right. Now, this will have some value for the limit, and there's three things that are possible. One is that the limit is less than 1, and when the limit is less than 1, this thing converges. The limit could be greater than 1 or infinity, and if that happens, then we have divergence. And if the limit equals 1, then we can't conclude anything. We'll have to use a different test. So it's inconclusive if the limit equals 1. So, great. How does it work? Well, imagine we have this series. So the sum of the series from k equals 1 to infinity of this really messy rule. Negative 1 to the k plus 1 times 2 to the 2k minus 1 over k times 3 to the k power. What a gross rule. We'd like to know if this thing converges or diverges. And so the ratio test is a good test for this. The limit as n goes to infinity. And we want the absolute value. Now the n plus 1 term, so everywhere that there's a k, I'm going to replace that with n plus 1. So I have negative 1 to the n plus 1 plus 1 times 2 to the 2 times n plus 1 minus 1 power over n plus 1 times 3 to the n plus 1 power. And rather than dividing it by the nth term, I'm going to multiply by the reciprocal of the nth term. So times. So everywhere there's a k, I'm going to have an n, and I'm going to have the reciprocal. So my numerator will be n times 3 to the n over negative 1 to the n plus 1 times 2 to the 2n minus 1. And so I'm taking this funny looking limit and seeing what happens. So the limit as n goes to infinity. Now I'm just simplifying. I'm going to pay attention to the common basis. So I have negative 1 to the n plus 2 divided by negative 1 to the n plus 1. The bases are the same. I can subtract the exponents. N minus n is 0. 2 minus 1 is 1. So I just have negative 1 to the first power. I also have 2 to the 2n plus 1 power over 2 to the 2n minus 1 power. Bases are the same. Subtract the exponents. 2n minus 2n is 0. 1 minus negative 1 is 2. So I've got 2 squared times n, because that won't divide out. And then I have 3 to the n over 3 to the n plus 1. Bases are the same. Subtract the exponents. I'm left with 3 to the negative 1, or 3 to the first in the denominator. Nothing's happened to the n plus 1. So after just using some exponent rules to simplify, we're left with this. And this I can clean up just a little bit. Since we've got the absolute value, the negative 1 is negligible. and we're left with 4n over 3 times n plus 1. Since these degrees are the same, then the limit as n goes to infinity is just the ratio of the coefficients. In this case, it's 4/3. Now, because the limit is greater than 1, I can conclude that this series diverges. We'll do one more example.